Welcome to Unit 4 Chemisode. This is on Le Chatelier's principle, or Le Chat for short. A reminder that we have Edmodo, where you can get the notes for these videos. You can go iTunes there, where you can find the podcasts for these, the audio style. I haven't done a lot of them yet, but I'm going to kind of catch up on those, hopefully. And obviously the YouTube channel, which you're watching at the moment. Let's go have a look at Le Chatelier's principle. Okay, here's Le Chatelier. Cute little picture of a cat with a French beret on it. That's because Mr. Henry Le Chatelier, or Henri Le Chatelier, was a Frenchman who came up with the principle that we're going to learn about in this video. Here's basically all the things that you need to know about, all the key words you need to use in terms of Le Chatelier's principle, and we're going to discuss those hopefully within about 12 minutes. Let's go have a look at what the idea of Le Chatelier's principle actually is. Le Chatelier had an idea that when a change is made, a reaction will work to oppose that change. So if you do any of these things to a reaction, to a vessel which contains an equilibrium mixture, what will happen is the reaction will work to oppose that change that has been made. Change is bad for Le Chat. So let's have a look at how each of these things works in the idea of Le Chatelier. First of all, adding products or reactants. What Le Chatelier says is that when you add a product, what will happen is the reaction will move to oppose that change, and thus you'll move the reaction to the left and move away from the products towards reactants, and it will oppose that addition of your product. If you add a reactant, the reaction will move forward to oppose the addition of that reactant. For example, what we use are these types of graphs quite often. We use concentration versus time graphs. Sometimes we use rates of reaction versus time as well. You need to kind of be able to tell the difference between those two. But here's concentration versus time. Here we have an equilibrium mixture. Obviously we know it's equilibrium because the concentrations of these three things aren't changing. This is a Haber process again. I like to use that a lot in my explanations of Le Chatelier. We have a certain amount of hydrogen, a certain amount of nitrogen, a certain amount of ammonia in this mixture. If we add hydrogen to it, hydrogen is one of our reactants. What we expect to see is a reaction moving towards the right, where we have more ammonia being produced, and obviously the reactants decreasing in concentration. So add a hydrogen, initially increases, so straight away spike of hydrogen, and then slowly a decrease in hydrogen as the reaction moves towards the right, proceeds forwards. Obviously, right at the outset, when we add the hydrogen, the concentration of ammonia doesn't change, but it gradually increases as the reaction moves forward and re-establishing equilibrium. And obviously, because we didn't add any nitrogen, but obviously it's one of our reactants, it slowly decreases. Okay, so what happens? Production of ammonia, add extra hydrogen, equilibrium moves to the right, reactants start to decrease, products start to increase, and equilibrium is re-established here. Notice that the amount of hydrogen is still higher than what you started off with, but the amount of nitrogen is less because obviously that just decreased. These changes in equilibrium, or the changes as you're moving the curves here, are all proportional to the mole ratio in the equation. I probably should have the equation for this here, written here, just so you can see that the mole ratio of hydrogen, ammonia, and nitrogen is 1 nitrogen, 3 hydrogens gives you 2 ammonias. This will go down 3 times as much as the nitrogen because of that ratio. And obviously, the ammonia is going to go up twice as much as the nitrogen goes down because of that ratio, because of that 1, 2, and 3 ratio, because that's what the coefficients are in the equation. Hopefully that kind of makes sense to you. But addition of products reactants moves to oppose that change. Next up, we have our change in the temperature. This is one of the more interesting ones you can kind of think of. what happens is when you change the temperature of a thing, the reaction will move to oppose that change, and it depends on what type of reaction it actually is, whether it's an endothermic reaction or whether it's an exothermic reaction. The example I've got here is an endothermic reaction where energy is one of our reactants, where we're using energy. So the forward reaction here is endothermic. It's a positive delta H. What will happen, our change is decreasing the temperature. Okay, so our change is decreasing the temperature, we have an endothermic reaction. So according to Le Chatelier, the reaction will move to oppose the change, oppose the decrease in temperature, and thus the reaction will want to heat back up, and so an exothermic reaction will be required. The exothermic is our reverse reaction here. So our reaction going back this way is exothermic. So the forward reaction is endothermic, so a back reaction occurs because the wants to oppose that decrease in temperature, back reaction occurs. We end up with more reactants at our new equilibrium. So what we have here is obviously a concentration versus time graph. We reach equilibrium. This dotted line is our temperature decrease. And gradually our reaction moves to the left and we get more of our product and obviously less of our two reactants there. The amount of change again is mole ratio dependent. So obviously the carbon monoxide goes down twice as much as our oxygen and twice as much as our carbon dioxide goes up. So hopefully that makes sense to you in terms of the changes here. So a change in temperature, you get gradual changes in your concentrations. Okay. The shift of equilibrium relies on the heat of reaction. So whether it's exothermic or endothermic, you need to think about what was the change, how is Le Chatelier saying that the reaction is going to respond to that change. Okay, and that's the important thing about changing the temperature. Moving on, changing the pressure of a reaction. Okay, so changing the pressure of a reaction, the reaction will move to oppose the change by moving to the side with less gas particles. So this is involving really changing the volume of something. If you change the volume, you're going to change the pressure in it, so therefore it's going to move a certain way. So let's look at this equation where we have sulfur dioxide reacting with oxygen to form sulfur trioxide. This is a very fundamental thing in terms of the production of sulfuric acid rain, but you don't need to know about that for VCE. Let's have a look at it. If the change we're making is decreasing the volume of our vessel, which is increasing the pressure. Okay, so concentration versus time, obviously decreasing the volume of the vessel means we increase concentrations straight away. Everything increases in terms of concentration here. So immediately increase the concentration of all species. The reaction opposes this change by decreasing the number of gas particles. So if you decrease the volume, you increase the pressure, it moves to the side with the least number of gas particles, which happens to be our our products in this equation here, because our reactants here have 3 gas particles, our products have only 2. So decreasing the volume, increasing the pressure will push this reaction towards the right and then slowly re-establish equilibrium. So in this reaction, it moves to the right as there is only 2 gas particles on that side. So what happens in our concentrations? Our reactants slowly decrease again and slowly decrease again, and our concentration of our products increases. Thing to note is your concentration of your reactants is still greater than it was beforehand, but your yield of your reactant is better. Okay, so even though your concentration is still a little bit higher because you've decreased the volume, okay, your yield of sulfur trioxide is better. So when you're doing these graphs, you want to make sure your line goes still above where the initial equilibrium was in terms of concentration. Obviously, you've got less moles of your reactants, but your concentration is still more because the difference between concentration and volume and number of moles. Hopefully you can kind of get your head around that. But change in pressure, Le Chatelier says you'll want to try and oppose that change, and you think about how it's going to oppose that change by moving to the side with the fewer gas particles. Let's move on, and I think we got one more. Nope, that's it. That's the 3 changes you can make. There's a few different things here. Let's look at this equation here. Obviously, we've got aqueous A plus aqueous B going to aqueous C. What's going to happen if you change these things here? What happens if you increase A, increase B, increase C, increase? Is it going to have a leftward shift? Is it going to have a rightward shift? All right. Doing this, try and work out what's going to happen to these. Obviously, we're changing concentrations of each of these things here. So you have a think about what you think, where you think these things should go. If you increase A, what will happen? Leftward shift, forming more products. Rightward shift, forming more, leftward shift, forming more reactants. Rightward shift, forming more products, or no shift whatsoever. And I'll come back and we'll do this. I'll show you the answers. So, you're back now. Let's have a look at where these lie. If we increase the concentration of A, Le Chatelier says that we'll try and oppose that change and do that by moving forward. So that means it's a rightward shift. Increase B, same thing. Increasing reactants, want to oppose that, rightward shift would decrease that. Increase C, increase this, it goes backwards. Decrease A, if we decrease this, what Le Chatelier says, we want to oppose that change, so therefore C would break up and give you more A. So it would have a leftward shift there. Decrease B, leftward shift. Decrease C, you'd have a rightward shift. Okay, so obviously those ones are pretty easy. What does get more difficult is when you're changing 2 things, so either you're doubling A and halving B, or doubling both B and C. The easiest thing I can think of to explain this is to give values to A, B, and C. So what I do is I would give everything a value. Obviously write out an equilibrium constant or an expression for an equilibrium constant and give everything a value. So let A equal 2, B equal 3, and C equal 1. Just given those random numbers there. You can give them any number you like. Okay? You can give them all 1 if you want. It's up to you what you want to do. But let's have a look at what happens when we double A and halve B. So if we double A becomes 4, halve B, it becomes 1.5. Looking at that, we get our Q value as being 0.16. This happens to be exactly the same as our equilibrium constant. Because we gave this and said this was at equilibrium, if we change it, what happens to our K value? And it stays the same. What this means is there's going to be no shift. So this one gets put into our no shift column because our Q value doesn't change. If we double both B and C, alright, so that means C becomes 2 and B becomes 6. We plug this into our equilibrium constant, and once again we notice that Q doesn't change. That means there's going to be no shift whatsoever, so therefore doubling both B and C puts it into this direction here. Alright, so when you're changing things on both sides, it's probably nice to just do some maths and work out exactly what will happen due to changes in the K value, or the Q value, I should say, the reaction quotient, because K is a constant. When you change things, you are calculating the reaction quotient, which is Q. Okay, that's the first one. Let's look at this next different system. We have I as a gas forming our Z gas. If you add more X, remove some X, increase the volume, decrease the volume, what's going to happen to these things here? According to Le Chatelier, where will these things go? Will they be a leftward shift, where you're producing more reactants, rightward shift, producing a better yield, more products, or no shift whatsoever? Give you 2 seconds or 3 seconds to look at this, pause it if you need to, work out where it's going to go, and then we'll come back and have a look at it. And you're back again. Let's have a look at where these go. Adding more X. Obviously adding more X will push it forward. Removing some X will make it go backwards. So those are pretty simple. That's just obvious Le Chatelier things, like increasing this, you'll want to decrease it, so it goes forward, so on and so forth. Pretty easy. Opposing the change each time, you're writing down that it's all about Le Chatelier. You want to say that an increase in X, according to Le Chatelier's principle, you'll want to decrease that change or oppose that change, so therefore you'll have a forward reaction or a rightward shift in equilibrium. Now, increasing the volume, decreasing the volume. Obviously, these two things have to do with pressure and how many gas particles there are on either side. Increasing the volume decreases the pressure. So what you'll want to do is, Le Chatelier says, increasing the volume will decrease the pressure. Le Chatelier says we want to oppose that change, so therefore we'll produce more gas particles to fill up and negate that increase or decrease in pressure. So increase the volume, you'll want to go to the left because there are more gas particles on the left hand side. There's 3 gas particles than on the right hand side where you have only 1. So what happens, we go to the left. Increase the volume, go to the left because we're decreasing our pressure. Decrease the volume obviously is the opposite. Decrease the volume means you're increasing the pressure, means you're going to go to your right. So therefore, it's a rightward shift. Now, interesting thing here, one thing I do need to point out is in terms of changing pressure, if you add an inert gas, that doesn't do anything to equilibrium. So if you have a cylinder or if you have a container and you increase the pressure by adding an inert gas, that doesn't change anything. Just that's something to note as well. That's only when you're changing volume and pressure changing because you're changing concentrations. Let's move on anyway. Let's do a summary. I think it's a summary now. Yep, summary. Reactions do not reach, not a summary. This is just the next part. Some reactions do not reach equilibrium. That's when the products can be lost. If you have a constant losing of products, you're going to have a forward reaction always occurring. So for instance, if you have an open system where you're producing a gas and the gas is just getting bubbled off, okay, products are constantly being lost, so therefore you're going to continue until that reaction finishes. Removal of one compound from the equation, obviously, that's another thing where products might be lost, so therefore you're going to be constantly moving forward with that reaction. So the forward reaction goes to completion when the products are lost or you remove a compound from the equation. That's where you don't get an equilibrium. You get a complete reaction happening. Moving forward, we have, I think we've got a summary now. No, we aren't. We've got an example of hemoglobin. This is how we can use equilibrium in our bodies, understanding how we can change a couple of things. Basically, we have 2 competing systems in our bodies. We have hemoglobin plus oxygen goes to oxyhemoglobin. This is how we move oxygen around our bodies. It attaches to our hemoglobin, and that's what happens. This has got a relatively small K value, so therefore a relatively small amount of oxyhemoglobin compared to other stuff. In your lungs, you breathe in a lot of oxygen, so therefore you have a large concentration of oxygen, therefore we get a lot of oxyhemoglobin produced. As it moves through your body, okay, into your muscles and into your organs, you got less concentration of oxygen, so therefore the reaction goes backwards and oxygen gets released for use. So that's kind of how you can use this in your body, where you have how oxygen gets transported around and gets released into your body because of this equilibrium process. In your lungs, you got lots of that, so therefore we go forward. Your blood takes this around to your organs where we have less oxygen, so therefore it releases it back out. That's how that works. Carbon monoxide poisoning actually works by having a very large K. So as soon as carbon monoxide gets exposed to hemoglobin, it latches on and basically takes hemoglobin out of the equation. So as you put carbon monoxide in, what you're doing is you're removing hemoglobin from this reaction here. So therefore we get less oxyhemoglobin, so therefore got less oxyhemoglobin to move around and deliver oxygen to where it's needed. So basically, carbon monoxide wins the fight over oxygen, okay, and thus you die. Problem is, or not a problem, it's probably a good thing actually, this is always reversible. So if you see someone who's suffering from carbon monoxide poisoning, say they're sitting in a car park with doesn't have nice extractor fans, and you see them starting to feel a bit faint because they have got too much carbon monoxide, if you just remove them from the source of carbon monoxide, it decreases the amount of carbon monoxide, so therefore this reaction goes backwards. So therefore we have more hemoglobin to react with our oxygen to go forwards and form more oxyhemoglobin. So basically you can reverse and go forward with your reactions based on changing the concentrations of your products and your reactants. So that's kind of a real life example of how we can use Le Chatelier's principle and save lives from carbon monoxide poisoning. Obviously, it's not a good thing. Carbon monoxide is very, very dangerous, but this is the idea behind it, how it all works. Now we have a summary, surely. Yes, we do. Summary of Le Chatelier. When a change is made, the reaction will move forwards or backwards to oppose that change. All changes are made to re-establish the equilibrium constant apart from a change in temperature. So whenever you change something, your reaction will move to re-establish the equilibrium constant. The only time you do not re-establish the equilibrium constant is when you change the temperature. So what the idea is, when we're looking at equilibrium and changes in equilibrium, we always want to refer back to Le Chatelier's principle. So we want to say, this was a change. Le Chatelier says we want to oppose that change. How will the reaction cope to oppose that change? Worst case scenario, give some numbers into your equations and base it around re-establishing this equilibrium constant. If your new numbers give you a larger equilibrium constant, you'll try and move backwards. If you have new numbers produce a lower equilibrium constant, you'll try and move forwards, so on and so forth. That's your summary. But always refer to Le Chatelier's principle. Always say, this is a change. Le Chat says we want to oppose that change. This is how we're going to do it. They're your three things that you need to say in your answers. All right. Now, the next video is on acidity constants. I think I said that last time, but I guarantee you the next video is on acidity constants and acids and bases. Take it easy, and I'll see you then.